Welcome back to Fun Facts Online. Today, we are abandoning the theoretical and stepping into the industrial. We are talking about the single most complex engineering challenge currently being tackled by the human species, magnetic confinement fusion. You have heard the headlines. You know the promise: infinite clean energy, fuel found in seawater, no carbon, no long-lived radioactive waste. But for decades, fusion has been the technology of the distant future. That narrative is dead. As we move through late 2024 and into 2025, fusion has shifted from a science experiment to an industrial race. We are no longer just trying to light a match, we are trying to keep a flame alive inside a hurricane. Today we are going deep into the physics of the impossible, the architectural rivalry between the donut and the twisted ribbon, and the massive infusion of private capital that is building the star in the bottle. Let's start with the fundamental problem. Why is this so hard? It comes down to the vessel. To make fusion work, you need to heat isotopes of hydrogen, usually deuterium and tritium, to 150 million degrees Celsius. That is 10 times hotter than the core of our sun. At these temperatures, matter ceases to be a solid, liquid, or gas. It becomes plasma, the fourth state of matter. Plasma is an ionized soup of stripped electrons and naked nuclei buzzing with electric charge. Because it is charged, we can trap it using magnetic fields. This is the concept of the magnetic bottle. But plasma is not a well-behaved gas. It is chaotic. It has a personality. Imagine trying to hold a balloon made of jelly together, using only rubber bands. If you squeeze too hard in one place, it bulges out in another. If you have a weak spot, the whole thing explodes outward. In fusion, these bulges are called instabilities. One of the most notorious adversaries we face is the edge localized mode, or ELM. These are essentially solar flares that happen inside the reactor. They are violent bursts of energy that erupt from the edge of the plasma. If an ELM hits the interior wall of your reactor, it can melt solid tungsten tiles in milliseconds. So the challenge of the 2020s isn't just creating plasma, it is sustaining it by taming these instabilities. To understand if a reactor is working, you have to look at the Lawson criterion. This is the trifecta of fusion. You need three things simultaneously. First, temperature. You need that 150 million degrees to overcome the electrostatic repulsion between atoms so they can fuse. Second, density. You need enough particles in the soup to actually collide. And third, confinement time. You have to trap that heat long enough for the reaction to become self-sustaining. The history of fusion is a trade-off between these three. Tokamaks are great at temperature and density, but struggle with confinement time because they are prone to disruptions. Stellarators can hold plasma forever but struggle to get it hot enough. The current era is about breaking these compromises. Let's look at the hardware. The battle for dominance is currently being fought between two machine designs. In one corner you have the Tokamak. This is the Russian acronym for toroidal chamber with magnetic coils. It looks like a giant, hollow donut. The Tokamak uses massive external magnets to create a ring-shaped field, but here is the key. It also uses a central solenoid to induce a massive electrical current flowing inside the plasma itself. This internal current twists the magnetic field lines into a helix, which traps the particles. This internal current is the Tokamak's greatest strength and its fatal flaw. It heats the plasma efficiently, but if that current snaps, the magnetic cage collapses. This is called a disruption event. It slams the thermal energy of the sun into the walls with the force of a stick of dynamite. The current champion of this design is ITER in France, a 35-nation collaboration. It is a beast of steel and concrete, but it is slow. ITER recently announced a delay in full operations to 2035. This delay has effectively opened the door for agile private competitors to swoop in. In the other corner we have the Stellarator. If the Tokamak is a donut, the Stellarator is a cruller twisted by a surrealist artist. It does not induce a current inside the plasma. Instead, it relies entirely on external coils twisted into insanely complex 3D shapes to generate that helical field. Because there is no driven current in the plasma, Stellarators are immune to the violent disruptions that plague Tokamaks. They are inherently steady state. You turn them on, and theoretically they run forever. The problem has always been construction. Designing coils that twist in 3 dimensions with millimeter precision was impossible for decades. But supercomputers and 3D printing have changed the game. The Wendelstein 7X in Germany proved the physics works. And just recently, Princeton's Muse project built a Stellarator using permanent magnets and 3D printed shells, proving they don't have to be billion-dollar monoliths. This brings us to the space race of the 2020s. We're seeing a massive explosion of private capital, over $10 billion, funding a SpaceX for fusion approach. Let's break down the 3 leaders who are diverging from the government timelines. First, there is Commonwealth Fusion Systems, or CFS. Spun out of MIT, They are betting everything on a materials breakthrough, high-temperature superconducting magnets, or HTS. Traditional magnets need to be cooled to near absolute zero, around 4 Kelvin. CFS uses a new material called Rebco tape, rare earth barium copper oxide. This tape can operate at a balmy 20 Kelvin, but more importantly, it generates vastly stronger magnetic fields. In fusion, a stronger magnet means a smaller bottle. You don't need a building the size of a stadium if your magnets are strong enough. Their demo reactor, Spark, is under construction right now in Massachusetts. They are assembling the vacuum vessel and winding these HTS magnets as we speak, aiming for net energy years ahead of ITER. Then there is the dark horse, Helion Energy. They are taking a completely different path. They aren't using a tokamak or a stellarator. They are using a pulsed system called a field-reversed configuration. Think of a diesel engine. Helion's machine, called Polaris, shoots 2 rings of plasma at each other from opposite ends of a tube. They smash together in the center, compress, fuse, and then expand. But here is the killer app: direct capture. In a traditional power plant, you use heat to boil water, spin a turbine, and turn a generator. It's 19th century technology. Helion skips that. As their fused plasma expands, it pushes back against the magnetic field. By Faraday's law of induction, this change in the magnetic field generates electricity directly in the coils. No steam, no turbines. Backed by heavy hitters like Sam Altman, they are aiming to demonstrate electricity generation by 2028. It is an aggressive timeline that skeptics call impossible, but if it works, it changes the economics of energy overnight. Third, we have Tokamaks Energy in the UK. They are pioneering the spherical tokamak. Instead of a donut, imagine a cored apple. It's a more compact shape that can hold higher pressure plasma with a weaker magnetic field. Their ST40 reactor has already hit 100 million degrees, a record for a private company. They are also utilizing HTS magnets, specifically testing no insulation coils that are more robust against failure. But hardware is only half the battle. You need a nervous system. Plasma is turbulent. Controlling it with standard industrial controllers is like trying to drive a Formula 1 car on ice using only a stopwatch. You need to react to skids before they happen. This is where artificial intelligence enters the chat. In a landmark collaboration, Google DeepMind trained an AI to control the TCV tokamak in Switzerland. They didn't just tell the AI to keep it stable, they told it to sculpt the plasma into specific shapes, and the AI figured out which magnetic knobs to turn in real time. Even more impressive is recent work at the DIIID National Fusion Facility. Researchers from Princeton deployed an AI that can predict tearing instabilities, those rips in the magnetic fabric, before they happen. The AI sees the tear forming in the data and subtly adjusts the beams to heal the plasma. This self-healing capability is the key to moving from short pulses to continuous power. Finally, we have to talk about the armor. What do you build the walls out of? When you have a reaction that hot, the exhaust is brutal. The material of choice is tungsten. It has the highest melting point of any metal at over 400 degrees Celsius. But tungsten is brittle. Under neutron bombardment, it cracks. Scientists are now developing tungsten fiber-reinforced tungsten. It's a metal matrix composite, like carbon fiber, but made of pure metal to prevent cracking. And then there is the fuel cycle. We have plenty of deuterium in seawater, but tritium is incredibly rare. A power plant has to make its own. This happens in the breeding blanket, a layer of lithium surrounding the core. When a neutron hits the lithium, it splits into helium and tritium, which is then pumped back into the fuel. Companies like Kyoto Fusioneering are building test loops right now to circulate liquid lithium-lead alloys at 1000 degrees to prove this works. So where does this leave us? We are at a pivotal moment. The physics is largely proven. The challenge is now supply chain and manufacturing. Can we make enough HTS tape? Can we 3D print the parts with enough precision? Can we breed the fuel? Fusion is becoming a national security asset, with China, the US, and Europe vying for leadership. If successful, this isn't just another energy source. It is the baseload to complement solar and wind. It is the energy for data centers and heavy industry. We are building the nervous system with AI, the muscles with magnets, and the bones with advanced composites. Taming the sun is no longer a question of if. It is a question of when. And for the first time, when looks like it is within our lifetimes. Thanks for listening to Fun Facts Online.